Hi everyone, today we're back for an episode on oxygen not included, and today we'll try to understand better how the heat is transferred within the game. The heat transferred is affected by two factors, the thermal conductivity and the heat capacity. Today we'll be working mostly with liquids, but these two factors also apply to gases and solids. Each element has a different value for these two factors, so if for example here I take the salt water, we can see that the salt water has a thermal conductivity of 0.609 and it has a specific heat capacity of 4.1. If I now take a look at the liquid gold, we can see that it has a thermal conductivity of 6 and a specific heat capacity of 0.129, which is different from the salt water. So now what do these two factors mean? We'll start with the specific heat capacity and we'll try to keep it simple. So the specific heat capacity determines how much energy is required in order for an object to change its temperature, to see its temperature changed. So here, the amount of energy required to see an increase or a decrease of 1 degree per gram is 0.129 DTU. If we compare that specific heat capacity with the salt water that we've seen previously, we can see that the specific heat capacity for the salt water is 4.1 DTU, which is much higher than the liquid gold. It means that the salt water will require a lot more energy in order to see its temperature changed. It will depend on different factors, but considering that you use elements with the same thermal conductivity and the same temperature, that means that the salt water will require a lot more time in order to see its temperature change compared to the liquid gold. Let's now look at the thermal conductivity, and we can see that the salt water has a thermal conductivity of 0.609 DTU per meter seconds per degree. This represents how fast the element can transfer heat. So the higher it is, the faster the heat is going to be transferred, and the lower this value is, the slower the heat is going to be transferred by that element. If you want to transfer a lot of heat, you want to have a thermal conductivity that is high, but on the other hand, if you don't want to transfer a lot of heat, you want that thermal conductivity to be as low as possible. If we compare the salt water to the gold, we can see that the gold has a thermal conductivity of 6, which is much higher than the salt water, which means that the gold would transfer heat much faster than the salt water. To sum up our comparison between the gold and the salt water, the gold would take much less time to cool down or to be heated up because it has a low specific heat capacity compared to the salt water, and the gold would transfer heat much faster than the salt water because it has a higher thermal conductivity. Therefore, elements with a low specific heat capacity are cheap to change their temperature, to heat them up or to cool them down, and elements with a high specific heat capacity are fairly expensive to change the temperature, therefore to cool them down or to heat them up. A high thermal conductivity means that two elements with a very big temperature difference will not have that temperature difference for a long time, and they will have the same temperature very quickly because the heat will be transferred very quickly as well. Therefore, you want a high thermal conductivity if you want to cool down or heat up an element, and you want a low thermal conductivity if you want to see the different elements keep their temperature. There are buildings that allow us to modify that thermal conductivity, so they will allow us either to increase or decrease that thermal conductivity. So let's start with the pipes. We have the normal pipe. So the normal pipe will not affect the thermal conductivity. It will just leave the thermal conductivity of the material used as it is. So here we can see that it's using sandstone, and sandstone has a thermal conductivity of 2.9, and therefore there is a thermal conductivity of that pipe. If we look at the insulated pipe, we can see that it's using sandstone as well, but it now only has a thermal conductivity of 0.091. And that's because the thermal conductivity of insulated pipes is reduced to 3.125% of its initial thermal conductivity. And as you can imagine, 3.125% of 2.9 is 0.091. This is also valid for gas pipe, not just liquid pipe. So here we can see that the thermal conductivity of the gas pipe is 2.9, and the thermal conductivity of the insulated gas pipe is also 0.091. We've seen how to decrease the thermal conductivity of a pipe, but we can also increase the thermal conductivity of a pipe. And to do that, we will need to use radiant pipe. So that's the pipe here in yellow that you can see at the bottom. And this pipe will double the thermal conductivity of the material that it's using. In our case, we use gold, and we can see that our radiant liquid pipe has a thermal conductivity of 120. So now if we look at the properties of the gold, we can see that it has a thermal conductivity of 60, which is basically half of the thermal conductivity that our radiant liquid pipe has. The radiant gas pipe works the same way, but the radiant gas pipe cannot be built with the same material. For example, it cannot be built with gold, it can only be built with gold almanac. Therefore, it doesn't have the same thermal conductivity. So if we look here, we can see that our radiant gas pipe has a thermal conductivity of 4, and that's because the gold almanac has a radiant conductivity of only 2, as you can see here. There are still materials that you can use in order to build both radiant gas pipe and radiant liquid pipes. So if you look here, for example, there is the steel, the niobium, and the terbium, but these materials are harder to get. So for that reason, it's usually better to use radiant liquid pipes in order to cool down or heat up other elements. There are also tiles that will allow you either to reduce that thermal conductivity or increase it. The insulated tile that we can see here will allow you to reduce that thermal conductivity. So what does that mean? That means that the temperature inside of the room here will not change a lot, even though if the temperature that is outside of the room is very different, these two temperatures will remain more or less the same. So that means that there will be very little heat exchange between the temperature that is inside of the room and the temperature that is outside of the room. We also have the metal tile that will have a high thermal conductivity. So the metal tile by itself doesn't increase the thermal conductivity, but it's made of materials that have a high thermal conductivity. So here, as we can see, it has a thermal conductivity of 60 because it is made out of copper. So if we were to use that tile, that would mean that would be a big heat transfer between the temperature that is inside the room and the temperature that is outside of the room. So that would mean that very quickly the temperature that is inside of the room and the one that is outside of the room would match. They would both of them either decrease or increase in order to match and be at the same level. So now we see some examples. So here I have brine on the left and I have salt water on the right. So if we look at the property of the salt water, we can see that the salt water has a specific heat capacity of 4.1 and a thermal conductivity of 0.609. And we have brine that has a specific heat capacity of 3.4 and a thermal conductivity of 0.609 as well. That means that the brine needs less energy in order to see its temperature change. Therefore, if we try to cool it down, it should cool down faster. The brine should cool down faster than the salt water. So that's what we're going to try to see. In order to do that, I'm going to use polluted water in both of these tanks in order to cool down these two liquids. And this polluted water will be cooled down by an aqua tuner here and another one here on the right. So we can see that both the brine and the salt water are both at 25 degrees. So now I'm going to restart the game and we will see which one cools down the fastest. So it's going to take a little bit of time, so I'm just going to speed up the process. So I've sped up the process and we can see now that the brine has a temperature of 20 degrees 0.3 and the salt water has a temperature of 20.6 degrees. So the salt water was a little bit slower to cool down compared to the brine. In this example, we are going to try to cool down water, and to do so we will use two different coolants. We will use polluted water on the left side and we will use petroleum on the right side. The polluted water has a specific heat capacity of 4.179 and a thermal conductivity of 0.580, and the petroleum has a specific heat capacity of 1.760 and a thermal conductivity of 2. So the petroleum should be a better conductor than the polluted water, therefore the heat should change faster, but it should also absorb less energy because the specific heat capacity of the petroleum is lower than the specific heat capacity of the polluted water. So let's see that in action. So here we can see that I have polluted water that is coming at 5.8 degrees more or less, and I have petroleum coming at 6 degrees. So they will both cool down that water. And we can see that the water on the left is at 19.6 degrees, where the water on the right is at 19.5 degrees. So we can see that the water on the right cooled down a little bit faster than the water on the left, and that because the petroleum has a higher thermal conductivity compared to the polluted water. We can also see that even if both the polluted water and the petroleum enter at a temperature of more or less 6 degrees, when they leave that loop, they leave that cooling area, they don't have the same temperature. The petroleum has a temperature of 19.9 degrees and the polluted water has a temperature of 18.3 degrees, and that's because the polluted water has a higher specific heat capacity, therefore it can absorb more temperature with the same amount of water compared to the petroleum. Therefore, over time, the polluted water could end up cooling down more than the petroleum because it has a bigger difference in temperature between the water that it tries to cool down and its coolant, the polluted water itself.